which is this one right here. And it's an RLC circuit with the voltage taken off of the resistor. It's always taken off the resistor if you're building a bandpass of this style. And the output voltage is from here to here, plus to minus, from top to bottom. Okay, so first thing we want to do with this circuit is we want to discover what the resonant frequency is. And by doing this simple 1 over 2 pi square root of LC, if you dump in the inductor and capacitor voltage values that are shown up here, you can discover that it's 107 kilohertz. So this is not working in very low frequencies. It's up there around 110 kilohertz area. Now what we want to do to support the drawing we're going to make is to choose several frequencies that are located around 107 so that we can make a nice pretty plot when we're done. Okay? But how many? How are we going to do this? We lack the bandwidth. We need to figure out how many points we want to plot. If you're going to draw a picture that looks like this, you're going to want the resonant frequency. You're going to want the band, the minus 3 dB points. You're going to want a few points down here on the side that's rolling at minus 20 dB to give you enough points to plot a nice curve. And that's what this is all about. Part 1 is the calculations. Part 2, we'll actually sit down and do the drawings so that we can see how to do one. What we need to detect where the minus 3 dB points are is it sure would be nice to know where the bandwidth is on this circuit. So that'll help us pick the minus 3 dB points, the 0.707 points. And our first step in the process is shown below. At the resonant frequency, we're going to calculate X sub L, and we're going to calculate X sub C, which, guess what? They're equal at resonance, so you only have to do this thing once. And at resonance, we are assured to get the full 10 volts going through there because our winding resistance in this sample problem, as you can see up here, we've assumed the winding resistance to be 0 in the coil. In the real world, there's going to be some winding resistance to account for, and this is exactly where you would account for it, right down here in this little equation as you run your calculations. So, that being said, our winding resistance will assume to be only the resistance in the resistor. And this allows us, now that we've calculated 100 ohms and we have X sub L, this allows us to calculate Q, which is right here. And we discover that it's 6.72. And that directly affects the bandwidth equation here, which is dependent on the Q. And we end up with about a 16 kilohertz spread between the resonant frequency and the cutoff on the left and the cutoff on the right. What we're talking about is these 2 points. How far apart? How far apart is the bandwidth? It's about 8K to the left and about 8K to the right. Okay? So, if you take 107 kilohertz and you subtract about 8,000, you end up at 99K. If you add 8K versus subtracting 8K, you end up with 114.96, or if we want to estimate, 115 kilohertz for the sample of the problem. Now you might want to fix your notes to include the note here that this is 107 minus 8K, and this is 8 kilohertz plus 107. That's how we actually came up with those. So here's our 3 critical frequencies that we're going to look at, and we're going to add a couple of more At the end of the day, it turned out that 8 points was better than 6. So when we do this circuit, we're going to compute 5 times. 1, 2, 3, 4, 5 right here. We're going to compute 5 times exactly what's happening in the circuit at the given frequencies and calculate the output voltages, and then we'll draw a Bodie plot. Well, when I got done with the circuit, I was a lot happier, picking a couple of extra points, and so in the end, we'll use 8 points to draw a Bodie plot. It all boils down to calculating over and over and over. Here's frequency 1, frequency 2, and all the work that goes on in between. We need to calculate X sub L and X sub C at this given frequency of 10K. And we get 62 ohms, and we see that the capacitor is much bigger at the lower frequency, which we would expect in this curve. The cap dominates to the left, the inductor dominates to the right, and right in the middle, the resistor is the only component left at resonance. So once we've calculated X sub L and X sub C, and I want you to realize we do this over and over, see? We're going to do this like 5, 6, 7 times right now, over and over and over. We want to know what the cap and the inductor are doing at those frequencies. So here's the overall circuit that we're going to solve. I'm going to change colors. Woo! Screwed that up. Okay, there we go. I'm going to go with yellow. We're going to take this circuit right here, and we're going to calculate using voltage divider the actual voltage that appears at the output here called V out, where I'm circling, okay? The output of the filter. It's the power supply, which is 10, times the unknown resistance. Well, we do know what the resistance is. It's 100 ohms at 0, divided by this circuit, the inductor capacitor circuit. I just noticed that I called it the inductor resistor circuit, so I'm going to change that to L1C1 right here. You should fix your notes so that correction is available to you when you're going to need it. I'm looking for my sheet right now. If you'll just give me a second, I'll put this together in the computations area. L1, C1. There we go. Okay, back to business. If I plug in the impedance that's situated down here in yellow, up here at the top, I put it in as a big rectangular circuit. Just add it all up in rectangular. Because this is a series circuit, and you see the impedance can be done in polar and it can be done in rectangular. I chose to show you that I could convert them very quickly here into polar, but we could have left them in rectangular. It just would have made the line a lot longer, including the I factors and the magnitudes. So our first computation produces 0.1393 volts. We're not going to really be interested in the phase angle for the phase Bodie plot, so we could ignore those in all the calculations. Moving up in frequency to 99K, now we get to one of the 3 dB points, and you see in this location right here that the inductor and the capacitor are starting to change. The capacitor is starting to shrink in value. It's down to 731, and the inductor's gone up while the resistor remains the same. So again, we take the voltage divider equation down here and we compute the voltage sitting on the output V out right here, and we come up with 6.747. This is the voltage at our critical frequency. Okay, ELE 112, this is a video that is not necessarily part of any major homework assignment, but we're going to do the front end of something that you might have done in a lab, which is build a Bodie plot. If you forget what a bandpass Bodie plot looks like, you're going to be plotting for a resonating frequency at some value with a couple of cutoff bands, and we want to plot dBs versus frequency, and we're going to use semi-log, log-semi-log paper to do this. And so the starting point for any of these problems is you have to solve an initial circuit. As we migrate through and continue making our calculations that are sitting here on the page, we are actually hit with frequency 3, which is the other side of resonance, 115K. We compute X sub L and X sub C. We see that also they are reasonably equal there, although now the inductor is larger than the capacitor because the inductor dominates on the right side of resonance and the capacitor dominates on the left. So the output voltage is the power supply times the resistor divided by the series combination of the three components. Minus 90 for caps, positive 90 for inductors, 0 for the resistor, and we come up with 7.33 as our answer, and the impedance, as you will find out shortly, is going to be quickly gotten rid of. We really are just focusing on the magnitude of the calculations at this point, which brings up a good point. In this section, they show you some shortcuts on how to calculate these voltages without the phase angle by using the square root formulas of R squared plus X sub L plus X sub C, etc., etc. It saves you having to work with the phasor angles. That's about the only advantage. So if it was me, I'd continue working this way. Frequency 4, 1 megahertz. We calculate X sub L and X sub C, and we see that now the inductor is much, much bigger than the capacitor. And we've got our final calculation down here, which I didn't show to you, but I made it. It's 0.1611. And that gives us our 4 frequencies and our 4 magnitudes. Using the minus 20 dB log of V out over V in allows you then to calculate the 4 dB units. So although we could have done a plot showing these voltages here in blue, those numbers are not friendly. 0.1393, 0.1611, not friendly plotting numbers. But the dBs produce a much better spread, 37, 3, minus 2.5, minus 35.86. These points will plot on the graph a lot better, as you will see in the next video.